There we go. Hello.
All right, shall we? Let's play read along with the syllabus here. Woo! Okay, here we go. So, I hope you're here for Astrophysics 1. Looking at the crowd here, I would say that's a good possibility there. You know my email address. Well, there's my email address. You know where my office is. And I'm looking at office hours of 4:10 to 5:30, Monday through Thursday in my office. What was I going to say? Note that 4:10 is right after this class, so sometimes it's like, oh, homework questions? Come on over. If you can't meet with me during my official office hours, please don't hesitate to set up an appointment for a more convenient time. Don't be shy about contacting me because I want you to succeed and I'm here to help. The text is Introduction to Modern Astrophysics, or Bob, the Big Orange Book, as in if you have a physical copy. It's like 1,400 pages. It is a brick. I sent an email to you folks. Did anybody opt in to BibliU? Because Dr. Trees and I were betting nobody would. It was like an upper level student. But in any case, for this class at least, it makes more sense not to because it's cheaper to just get the book once. I do kind of like that I can access an electronic copy of it now because it's big and heavy and all that. Accessibility accommodations, if you have or think you may have a need for accessibility accommodations, please contact the accessibility service offices. And by the way, the printout is broken, it's not going anywhere. I might tap the link there, but I promise online that will work. To arrange a confidential discussion regarding equitable access and reasonable accommodations. If you're registered with accessibility services and have a current letter requesting reasonable accommodations, please contact me as early in the semester as possible to discuss how accommodations will be applied in this course. Course overview. This is the first in the 2-semester astrophysics sequence. We'll begin by studying celestial mechanics, which is the study of orbits in a gravitational field. This is important because it's the key to determining the masses of stars and other celestial objects. Turns out you can't put them on a scale, but we can weigh them, quote unquote, by using orbital mechanics. Primary means by which astronomers study astrophysical phenomena is by collecting light and other forms of electromagnetic radiation from them. With this in mind, we'll review what you learned in contemporary physics about the wave-particle duality of light, black-body radiation, and the interaction of radiation with atoms. Why, then at this point, we'll be ready to apply what we've learned to a specific astrophysical problem, the determination of the masses of stars in binary star systems, in which two stars orbit one another due to their mutual gravitational attraction. The physical properties of stellar atmospheres are determined from the appearance of their spectral lines. To understand how this is done, we will study how spectral lines are formed. This will require an understanding of the Boltzmann and Saha equations from thermodynamics, which describe the relative populations of different atomic energy levels and ionization states, respectively. Then we'll use what we've learned to understand the Hertzsprung-Russell diagram, a plot of stellar luminosity versus surface temperature. After that, we'll study stellar atmospheres and the physics of radiation transfer. Good stuff, in my opinion, and my opinion is correct. Next, we will study the equations of stellar structure that describe the balance between the inward pull of gravity and the outward push of pressure, and the transport of energy from the core to the surface. We'll learn how computers are used to create models of stellar interiors. Exams. There will be 2 exams during the course semester and a comprehensive final exam. First exam will be the week of September 29th, unless we decide it isn't, but that's what I have at least officially now in the syllabus. That's week 7. The second exam will be the week of November 3rd, week 12. The final exam will be comprehensive and will take place on Tuesday, December 9th at 7:30 p.m. This is a class that's not in a standard time slot, but I figured that I would make our exam on the day where nobody had a conflict, because that, I'm just using the 2:40 to 4:10 time slot. So homework problems will be collected on a regular basis and will be due on Wednesday. That might be a lot, but right now I'm thinking Wednesday evenings at 11:59 p.m. But hold on, maybe I'll change my mind, I haven't decided yet. Anyway, late homework will incur a 25% penalty. And the other thing is, sometimes it's like, you know, you're taking some other class and they're due on Wednesday too, so I'm flexible with that, we'll figure it out. We'll incur a 25% penalty if it's turned in by 11:59 p.m. on the following Monday. I would prefer that you write out your solutions by hand and then scan them to a PDF file. A lot of you have been doing that for me before. That you email me as an attachment. You can, of course, use a standard scanner for this, or you can use a phone or tablet app that uses your camera to create a scan. Adobe Scan's the one I use, although I just downloaded PDF Gear, which is highly regarded. There's CanoScan, there's various ones. Pick your poison as far as that's concerned. It is good and it's free and it doesn't place a watermark in your documents. You can find others on the Google Play Store or the Apple App Store. You're allowed to use Mathematica when doing homework problems, and if you do that, send me your Mathematica notebooks. Academic integrity, one of the most important ways that astrophysics students learn how to think like an astrophysicist is, of course, to do the homework. But for this to be most effective, you need to fully engage with the problems, thinking through the parts that at first are not clear and turning them over in your mind as you seek clarity. Often your best learning and understanding will come about when you finally figure out how to solve a problem whose solution had at first eluded you. If you give up too early or take shortcuts, you'll never develop a deep understanding of the material, and sooner or later this will inevitably catch up to you. We're trying to develop mastery here, that's our goal. One shortcut that it can be tempting to take is to use shortcuts as solutions that you find online, either those from the textbook publisher posted on a website illegally, this is always a violation of copyright, or solutions produced by a company like Chegg. Looking at Chegg solutions after you turn in your assignment is fine and can give you additional insights. But the solutions I will post are usually better, just saying. I put lots of love and care into my solutions, I'm just saying. But using them to quote-unquote do your homework shortcuts your learning, and deprives you of the opportunity to develop the deep understanding that comes from figuring out how to solve a problem yourself. The same can be said for using an AI large language model, LLM like Gemini, Claude, or ChatGPT. Also note here that at least at this stage, such models often very confidently spit out garbage solutions that may seem reasonable to you if you don't understand how to do the problem, but it'll be pretty obvious to me that you took that route as a result. With these considerations in mind, you're not permitted to use online solutions or solutions generated by AI doing your homework. I know there's this dilemma, right, where companies say, we want you to have AI skills for us to want to hire you. And then, you know, your professors often say, if you use AI, I will fail you. But here, the goal is to develop mastery, right? And so you want to be able to recognize if the AI is telling you nonsense. You want to be able to understand things deeply on your own. And also, you're probably aware there's a lot of, I see lots of use for AI. It does have some negative environmental consequences and is driving people's electric bills up because of the demands on data centers and so forth. But in any case, just for fun, I will show you an example of an AI hallucination, if you will, or at least not doing a good job, where I gave ChatGPT, and this was like a year ago, so I don't know, maybe it's better now. But the other thing is you get different answers every time, potentially, because of the way these things work. So I gave it a problem from Mastering Astronomy, that I use in Astronomy 111. A newly discovered planet orbits a distant star with the same mass as the Sun and an average distance of 102 million kilometers. Its orbital eccentricity is 0.2. Find the planet's orbital period in years. So there it goes. And so blah, 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 blah. And it all looks pretty convincing, and if you don't really know what you're doing, wow, and so finally here we go. So we plug into these wonderful formulas, and I've shown you all the steps, blah, 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 blah. And the answer is 2.13 years approximately. I hope this helps. Let me know if you have any other questions. Well, the thing is, does anybody know how far Earth is from the Sun in kilometers approximately?
I know in miles,
Okay, what's it in miles?
I think 93 million.
It's about 93 million miles, which would have won you $1 million once on Who Wants to Be a Millionaire. That actually was the $1 million question. I'm watching the show, I'm like, oh my God, why can't I be in the hot seat right now? The person did win the $1 million. Now, if I had been on the show, I wouldn't have gotten that question, because the question, you know, the $500,000 question was something like, what color was the Pope's shirt in the painting blah, blah, blah from 1306 or something like that, you know, right? But still, in any case, in kilometers, that's about 150 million kilometers, which you will surely know after you take this class here. That's the so-called astronomical unit. This planet is 102 million kilometers from a star that's the same mass as the sun, so it might as well be the sun. And if you know anything about orbits, a planet whose average distance from the sun is less than that of the Earth has an orbital period which is smaller than that of the Earth, so I don't have to look at any of this to know that 2.13 years could not possibly be the correct answer. And that's, you know, you probably run into this too with AI. Sometimes it gives you the right answer and it's great, and sometimes it doesn't. And if you know what you're talking about, you can tell the difference, but if you don't know what you're talking about, these things lie very convincingly and confidently. And so, do you all know who Dr. Oz is? So he's a TV personality, he's a legitimate cardiac surgeon, he's a good cardiac surgeon, who also likes, he falls for a bunch of woo, a bunch of nonsense. You can be an MD, a very confident MD, who believes garbage about medical issues and so forth that are not your specialty. So he had a television show, I don't think it's on anymore, where it would be this mix of good, sound health advice and utter woo-woo nonsense. And you know, he said both of them with equal conviction, and if you don't know any better, you can't tell the difference, right? And that's my problem, like with these AI overviews, right, that you get in like Google search and so forth, is if I know what I'm talking about, I can tell when it's like, I'll be like, or yeah, that's good, well done. If it's not my field, I can't tell, right? Because it sounds equally convincing, you know, all it's so just, and you, again, you probably know this yourself, right, already, careful, right? Because you just can't tell when these things are making things up, you know, they're hallucinating, they're not sentient, as far as we know. And so just from the way they work, they can hallucinate, right, as you know. And well, here's a good example of that. So that's a word of caution there anyway, you know. So my point then is you want to be at the point where you could look at this like I did and say, I don't even have to look at the rest of those calculations, you know. I understand this, and that can't be right. Don't have to leave square one, and that cannot possibly be right. So that's my little AI soapbox here. And again, it's not that I think you should never use AI for anything, but for, you know, for what you're trying to do here is to master this material, you can't let AI make your answers for you. It just doesn't make any sense to do that. So you're supposed to love this, and you want to learn all about it. So you don't want AI to do your thinking for you. You want to think for yourself here. And come talk to your friendly professor, and get inspiration and stuff you're stuck on and all that sort of thing. Collaborating with other students is a legitimate way to work on homework, as long as you are genuinely sharing ideas and approaches with one another and not simply copying one another's math. Do not give another student a copy of your solutions or a draft of them, or look at another student's solutions or a draft of them. You should not be working with other students when you're writing your solutions out, or while using Excel or Mathematica to solve a problem. Failure to follow these guidelines may result in prosecution for academic dishonesty, which unfortunately I have done before. Dr. Andrick wrote a good guide to working homework problems in academically honest ways. It's available here. Again, this printout's broken online on Blackboard. It's there. In fact, I have a separate link for it on Blackboard. And via link on Blackboard site for this course. Grading all of your work. Each exam problem, each homework problem will be graded on a 4-point scale, which you can think of as being like a GPA. 4 points is an A, 3 is a B, 2 is a C, 1 is a D, 0 is an F. The relative contributions of the homework and exams to your final grade will be as follows. The regular exams are 25% each. The homework's 20% cumulative. The final exam is 30%. Of course, if you don't do the homework, well, it's not going to help you on the exams either, for sure. I will say you'll find that I know this is like, a physics class, but you'll see some essay questions on the exams too, because I want you to be able to explain concepts and processes and so forth. One of the things that, astronomy is a branch of physics, but one of the things about it that makes it different is that we talk about natural history, if you will, in astronomy. How the universe came to be, how stars form and stuff like that. And so you need to be able to tell stories, because that's ultimately what we're doing, is telling stories about the universe around us. And so I want you to be able to explain things. And those of you who had to make for like Physics 280, you know that, for example, with the photoelectric effect, it's entirely possible to do a problem about the photoelectric effect and have no idea how to explain how it works. And so I made everybody, and I was like, you're going to be able to explain this. And so I made everybody explain it on one of the exam problems. Boy, I spent a lot of quality time in office hours as a result of that, and was happy to do it. So they're kind of similar here. Your final letter grade for the course will correspond to the average GPA obtained from all your work, weighted as given in the table above. I modified the translation from GPA to grade a bit from the way it's done in your transcript to keep A's from being too hard to get, and be a little unrealistic to say, well, if you want an A, you need a 4.0 average on everything. Do not make any mistakes. The entire class, no, that's not how I do it. To make A's from being too hard to get, and B's and F's from being too easy to avoid. I mean, conversely, if you're getting 25% on everything, that ain't good either. So the table below shows how it works. Dr. Harmon, do you curve? It turns out years of experience show this makes a curve. It kind of makes what I would do if I curved anyway, pretty much. So letter grade, A plus is a quote-unquote GPA more than 3.8 or more. A is 3.5 to 3.79. A minus is 2.35 to 3.49. Now, if you finish with a 3.34 and you've been showing up for class, etc., well, there is a plus minus on the measurements of grades, and so I give you the benefit of the doubt, if you're close to the order there. So basically, if you get a 3.35, you're guaranteed an A minus. You're not guaranteed it if you get a 3.34, but just to probably get it. There's some slip there as far as that's concerned. If you never show up for class, they'll be like, I don't care anyway. But I think you all show up for class, right? You'll be here. B plus, 3.2 to 3.34. B, 3 to 3.19. B minus, starting to look like a report card now. 267 to 299. C plus, 234 to 266. C, 20 to 233. C minus, 18 to 199. D plus, 17 to 179. D, 16 to 169. D minus, 15 to 159. F, below 1.50. I don't think we're going to have any of those, but I'm going to put them in here anyway. And so at this point, I always try, I'll try to always say, instead of, do you have any questions, it's, what questions do you have? What are your questions, to convey the notion of, well, of course you've got questions. You should ask them, as opposed to, and so I do find that that's somewhat more successful when people actually speak up with their questions. Maybe here, maybe not. What questions do you have? What are your questions? Yes?
So for like scanning homework, that's like different than just taking a picture of our notebook, right? Is there...
Yeah. So using one of those apps, it takes a bunch of pictures, but it's fancy in that, your page may not be exactly rectangular in the camera frame, but like they'll draw a box around it, and then they'll apply a mathematical transformation to make it a nice rectangle. And then when you're done, they'll put all those images into a PDF document, which then you can send to me as a PDF. And then I take that, and I use my favorite PDF application, I guess, because it's on my computer, or there's an app version of it too. Foxit Reader, where I can mark everything up and put comments and all that sort of thing. So, yeah. Yeah, so don't just take pictures, because then you send me a bunch of pictures, and I'm like, thanks, you know. So yeah, use a PDF scanner. Again, there's a lot of good ones. PDF here is good. I played with it a little bit. And it's got like AI features with optical character recognition, so it can do things like, you know, it can produce an AI summary. You know, the person who was reviewing it is like, said, you know, sometimes the summary was good, sometimes it's like, okay, it's obvious this thing is not sentient, but anyway, you can do things like that. Adobe Scan is good, Canva Scan is pretty good, so there's various sort of things like that. So find one that can do that. What other questions do you have? Okay, let's see, did I have anything else to say? I don't think so. Let's get started learning celestial mechanics, shall we?
Yes.
Yes, yes, let's do this. All right, so, and by the way, all my lecture notes are posted on Blackboard, and also all the slides are posted on Blackboard too. So if you want, you can print out the slides and decorate them. Although mostly, I do tend to be chalk and talk and pretty pictures in this class, but lots of chalk and talk. And so, you know, some people like, oh yeah, I'll just print out the lecture notes and then decorate them, but other people are like, no, it helps my understanding if I'm actually writing things down as he says them. Yes, question?
Whenever I tried to access the lecture notes,
Oh, yeah.
Oh, did it write without you need
Yeah,
permission?
Access, yeah.
Oh, you should have done what you should have sent me a thing like, can I have access, please? I just need to turn it into everybody can have access to it. Yeah, I'll do that. In fact, do you want me to do it right now?
Sure.
Sure, okay. Let's see. Alright, so here's the nice and then you make a new right here. New window. No, don't make it over. No, don't make it over there. Okay. Okay, come to Papa. Let's see. Okay. Do that. And now come over. Which way is it? It's this way, yeah. It's always weird because it's most natural for me to put this on my left, but then it's really this thing's, it's on its right, and so I'm like, but in any case. Okay, so let me fix this. Try it out, Google.com. I need access. I need, damn it. I think it's looking for a particular file. Okay, drive.google.com space. Okay, there we are. And let me see, forgive me, I just need to talk through this here. Let's see, I'll go to start. I don't need to, but you know, I feel like I'm afraid of dead air, right? So, and then 2025 Fall Astronomy 310. Oh, so no, it's in a different folder. It's in the General Astrophysics Goodness folder. So courses. Well, the courses. Oh, it's still too high. Okay. Courses. Astrophysics. And astrophysics lecture notes. And let's see. I don't remember if there's a way to select all and change all the permissions or not. So for now, I'll fix the rest of them later. I'll just fix the chapter 2 lecture note permissions here. So, share. Share. So what is it set to now? Loading, loading, loading. Slowly, slowly. Slowly, 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 slowly. Sorry, Sharon. Shut the hell. Sorry, Sharon is unavailable at this time. Excuse me. Share. Share. Moving. There we go. Ah, restricted only. Okay, so I'll change this to Ohio Wesleyan University. And then I'll say done. And then can you try now to access it? Cool. Okay, excellent. And then I'll do the same thing with the slides.
The slides are fine.
Oh, the slides are fine. Oh, okay. All right. So it should work now for these lectures.
Thank you.
Okay, absolutely. All right. So back to our story. Where is everything? Let's see. Where's the other window? Uh-oh, where's the other window? Chapter 2, Celestial Mechanics. There we go. Okay. So, so this is, and here's where I mispronounce his name because, but basically I hear something similar to Tycho Brahe, right? People will say Tycho Brahe and stuff like that, but I think it's closer to Tycho Brahe, who lived from 1546 to 1601. He was the greatest naked eye astronomer of all time. Not coincidentally, because, note the date there, 1601, Galileo started using his telescope on, oh, I'm that guy, started using his, by the way, don't be obnoxious and have your phone be like, making noises during class or anything. I mean, who does that, right? He died right before Galileo, who did not invent the telescope, but was the first to systematically turn it to the heavens and promulgate his observations and so forth widely. So that's the trick to being the greatest naked eye observer ever, is be the kind of the last one who was an astronomer using, to any great extent, naked eye. But there's more to it than that. He got the patronage of the Danish king, who granted him an island, the island of like Ven, something like that is how it's said, where he could build his Uranoborg astronomical observatory. So he was flush with cash to build, for example, giant quadrants. So this is a quadrant where you would sight along a tube and you could read off angles and stuff like that. This is obviously, by the way, not meant to be to scale. But anyway, he was dedicated to making observations of positions on the sky as accurately as he could. And in particular, he was interested in documenting the movements of the planets amongst the stars. Now, he hired an assistant, Johannes Kepler, after whom a certain space telescope was named. And his assistant, Kepler, was a mathematical genius who noted that Tycho's observations of Mars in particular differed from what you could obtain from assuming circular motions by up to about 4 minutes of arc. Now the moon, so what's a minute of arc? Do you remember?
Is it 1 person?
No, not that. So it's an angle. A degree is what fraction of a circle? How many degrees in a circle? 360, right? A minute is a fraction of a degree. What do you think a fraction of 1 minute is? What fraction of a degree?
A 60th?
It is a 60th, yes. It didn't have to be, but it's kind of, a minute is a 60th of an hour time-wise. An arc minute is 1/60th of a degree, and an arc second is 1/60th of a minute, and therefore 1/3600th of a degree. And so we often use those to specify angles. So if he tried using circular motions to explain the position of Mars, Tycho, whose observations he trusted because he knew Tycho was very careful, it wasn't just measurement error here, they could be off by as much as 4 minutes of arc. The moon is half a degree, 30 minutes of arc across on our sky. So that's like, an eighth of the size of the moon on the sky. And so he decided that there must be something wrong with assuming circular motions. And story goes that, I think it was like his now I'm forgetting the story, but I think like his wife's family made wine and they used elliptical casks to store it. And anyway, what he realized is that actually planets move on ellipses rather than on circles. And so we will talk about Kepler's 3 laws. So Kepler figured out what planets do. Later on, Newton, with his theory of gravity, was able to explain Kepler's laws. Kepler's laws are a consequence of Newton's laws of motion plus his law of gravity. But for now, we'll stick with the what, and later we'll get to the why. So Kepler's first law, which he published in 1609 in a book called Astronomica Nova. What would that mean? What's nova mean?
New.
Yeah, new. So Astronomica Nova is like the new astronomy, right? The orbit of a planet is an ellipse with the sun at one focus of the ellipse. The other focus is empty. So, of course, we've got things to define here. So a circle is have you all heard the fancy name locus of points before? It just means set of points, basically. So a circle is a set of points that are all the same distance from a fixed point, called the center, right? An ellipse so a circle is just a special case of a more general kind of oval shape, called an ellipse. So with an ellipse, the idea is that an ellipse, instead of all the points are the same distance from a single point called the center, instead it has 2 special points, 2 points each of which is a focus, the plural of which is foci, not focuses. So I used to drive a Ford Focus, and I discovered that there were like online groups of Focus owners, and I was happy to learn one day that they in fact would talk about, if you have a bunch of them parked together, that's a bunch of foci. They were actually using the proper plural, so that made me happy. You all know about the cult of the Volkswagen, or as we say here in America, Volkswagen. So, you've heard me say this before, is it? Yeah, so I learned from one of my sisters that Volkswagen owners will do things like beep beep if they see one another, or give a thumbs up sign, stuff like that. So I call that like the cult of the Volkswagen. And recently, my wife and I rented a Jeep because we were going up to Ann Arbor to help her brother move some stuff out of a storage room. And we learned that there's also a cult of the Jeep. Do you all know about Duck Duck Jeep, right? Yeah, I did not know about this. So on the way up, we went to the Meijer in Bowling Green, Ohio, right? BGSU, home of BGSU, Bowling Green State University. And I see this other Jeep that happened to be parked near, and this young woman who probably was a BGSU student who gave off an aura of joy. She's a very sweet person. She comes up to me with this little red duck, and she says, I think that this red duck would look very nice with the color of your Jeep. And so she hands it to me, and I said, well, that's very sweet of you. Thank you very much. I had nothing to give back to her. My wife is like, how do you not know about the like Duck Duck Jeep and stuff like that? I'm like, why would I know this? She had just recently learned about it herself. Apparently, and I had never made this connection. Now I see it all the time. Many Jeeps have rows of little ducks on the dashboard, and I guess y'all are like, I know. It's a thing for them to exchange ducks with one another. I was today years old on that day when I learned that. So now I know. If you go in my office, you will see the little duck happily sitting on my shelf now, and my wife has ordered a little toy Jeep, and it's now going to be sitting on top of the little toy Jeep. So please enjoy that when you see that. And somehow I get from the folks side, that's right, yeah. It's like, how did I get to this? Oh yeah. As you know, I cannot be distracted. Laser-like focus on things. Anyway, the deal with an ellipse, what makes it an ellipse, is that the sum of the distances to the two foci is the same for every point on an ellipse. So no matter where I am, no matter what point you're on the ellipse, if you draw a line to one focus, draw a line to the other focus, and add up those two lengths, it's always exactly the same. That's what makes it an ellipse. And that means you can construct an ellipse with a pencil and a piece of string and two nails or thumbtacks or whatever. You nail them in place, stretch a piece of string taut between them, and with a pencil, trace out the curve that you get if you keep it taut at all times, and it'll naturally be true that's an ellipse because the total length of string isn't between the two foci, and the pencil isn't going to change as you move it around. So this is a way to construct an ellipse. If you move both the foci to the same point and do the same thing, you'll be drawing a circle. So a circle, every circle is an ellipse, but most ellipses aren't circles, right? In other words, a circle is just an ellipse where the two foci are coinciding with one another. They're on top of one another. There are, on an ellipse then, both a major axis, the long axis of the ellipse, and a minor axis, which is perpendicular to it, the short axis of the ellipse. And we call half the length of the major axis the semi-major axis. Guess what we call half the length of the minor axis?
The semi-minor?
That would be the semi-minor axis, as a matter of fact, yes. And there's a little bit of ambiguity that you have to figure out from context. We use semi-major axis to mean both the length of half the major axis, and we use it to mean the actual half the major axis itself. So you just have to know from the context, what you mean as far as that's concerned. And then we have a property called the eccentricity, which we'll get to in more detail later, which is related to how far away it is from a circle, if you will, where if the eccentricity is 0, it's a perfect circle. The larger you make the eccentricity, the more stretched out the ellipse is. And so that's what an ellipse is. Kepler's first law says that the sun is in one focus of a planet's orbit, and the other focus is empty, and the planet is tracing out an ellipse of a certain eccentricity. It could be anything. And the semi-major axis in principle could be anything. And that's how planets move. And by doing that, he was able to successfully duplicate Tycho's observations of Mars. And this is one of those things like, I can say that, and I'm still like, well, how did he figure that out? Right? But he did, because genius. So, what questions do you have? Yes?
Wait, just making sure I understand. The major axis is the entire thing.
Yeah, so you got the major axis is the entire thing. Semi-major axis is half of that. So there's sort of there's two semi-major axes that put together make the major axis.
I used to think that the major axis was the bigger half of like the ellipse that went around weirdly.
Nope. It's just you draw a line. It's like the largest diameter, quote unquote, of the ellipse. Okay.
Cool.
Yep. Mm-hmm. Yes. Okay. Gotta push the magic button. All right. So again, here's the idea. The sun lies at one focus, nothing lies at the other focus. There's the semi-major axis. And for things going around the sun, you've got perihelion is when the planet is closest to the sun. Aphelion on the other end of the major axis is when the planet is farthest from the sun. Right? Helios is Greek for sun, and so it's peri, close helion, close to the sun, aphelion. And if it's going around the Earth, we've got perigee and apogee. If we're talking about stars, it's periastron and apoastron in that case. But for the sun, it's perihelion and aphelion. Sometimes people say, well, what determines which focus has the sun and which one doesn't have the sun? The answer is whatever the initial conditions are that set up the orbit. That's what it comes down to. Okay? Can I push the magic button? Alrighty. So, what's the deal with this eccentricity? If we call C the distance from the center to either focus, they're symmetrically placed, the center to either focus, call that C. then the eccentricity is c divided by a, where a is the semi-major axis. And again, we say semi-major axis to mean, in this case, the length of half the major axis. So a, you'll see that symbol all the time, is the semi-major axis. C, you don't see that as much. Distance from the center to one focus. The eccentricity is just that ratio, c over a. So if we had a circle, what would c be? The distance from the center to either focus for a circle is what? It's what? 0, right? If it's a circle, I'm saying the center to either focus, the foci coincide at the center, so c itself is 0 in that case. So therefore, the eccentricity for a circle is 0, right? Because we're sitting on top of one another. Yes?
Does this mean that 1 is just a flat line?
It does mean that, yes. Yeah. At least in that limit. It's a little weird. It turns out that, and I'll get to this too, the circle and the ellipse are both conic sections. And the conic section that has an eccentricity of 1 is actually a parabola, it turns out. But in the limit of this ellipse thing here, yeah, you're right, it's a straight line. It's really a line segment, right? Because, in other words, if you imagine the foci moving further and further out until they're on either end of the major axis, and you imagine you're making this string construction, but you've got it such that you've pulled the tacks as far apart as they'll go, well then you just got a straight line. You're just tracing a straight line. So 0 eccentricity is a circle, and the bigger you make it, the squishier and squishier it gets. And in the limit, you'd be approaching 1 would be just the semi-major, just the major axis itself will be the ellipse. Degenerates into a straight line in that case, or a straight line segment. Yes, absolutely. Yeah. Very good. Okay. Questions, comments? I mean, what questions, comments, or observations do you have? Okay, on to Kepler's second law, also published in the same book. The line, this is 1609, the line joining a planet and the sun sweeps out equal areas in equal amounts of time. And note that if the amounts of time are not equal, then the areas are also not equal, because sometimes this is something, you won't do this, but it often happens that people misinterpret it as meaning something like the areas are always equal no matter what, which doesn't make any sense. In other words, it can't be that the area swept out in 1 trillionth of a second is the same as the area swept out in 4 weeks. You know, that doesn't make any sense. So it really says if the areas are equal, the times are equal, and vice versa. If the areas aren't equal, the times aren't equal. Half the area and half the time. A tenth of the area and a tenth of the time, and so forth. So equal areas and equal times. A line joining the planet to the sun sweeps out equal areas in equal amounts of time. And, well, what do you mean sweeping out area? What I mean is, imagine, so orbits are on a plane, an imaginary plane, and imagine you've got that the planet is connected to the focus where the sun is with an infinitely stretchy rubber band, and that infinitely stretchy rubber band has magic paint that can just keep generating, and as the planet moves on the table, so to speak, the orbit, that rubber band is squirting out paint and painting part of the table. That's what we mean by sweeping out area here. So, like the picture. So the idea here would be like, suppose that we've got a planet, or it could be a comet or anything, moving around the sun, and it goes from here to here. Well, here is the area swept out. That light blue is the area swept out. It really should be like, going to the center of the sun there, and we'll modify that a little bit later too when we realize, well, actually, the sun's not stationary because it doesn't have infinite mass, but don't worry about it for now. If it takes the same amount of time to go from here to here as it does to go from here to here, if those times are equal, those areas are equal. That's what Kepler's second law is saying. And so, as the words say, right, near perihelion at any particular amount of time, such as 30 days, a planet sweeps out an area that is short but wide. But near aphelion, in the same amount of time, a planet sweeps out an area that is long but narrow. The areas are the same, but notice that it has more arc along the orbit that it's moved in the same amount of time as closer to perihelion, because it has to make up for the fact that it's closer to the sun. I like to talk about a chef who is mathematically inclined, and so she proudly makes elliptical pizzas, and she slices them through one focus, and she wants all her customers to get a fair deal here, and so all her slices have the same area, but that means that some people get long, skinny slices, and other people get, broad, short slices that all have the same area because she's a show-off, and so she likes to do that, Anyway, that means we've got a corollary here. Planets move faster when they're closer to the sun. All right, it's a corollary of Kepler's second law, because when it's closer to the sun, to sweep out the same area in the same amount of time, it's got to move further. It's got to be moving faster than when it's further from the sun. What questions do you have? Can I push the button? I never hesitate to say no, please don't push the button yet, because I can talk faster than you can write, and so forth. So, alrighty? So you can download this yourself. At the University of Nebraska at Lincoln, they had a group there, they're no longer active, but they made all these fantastic simulations of various astronomical phenomena that they're largely targeted to intro astronomy, but you'll learn things from them. I learned things from them. They're great. I used to watch Bill Nye the Science Guy, right? Targeted at people in elementary school. I learned all kinds of stuff from that, and I was way past college, So I downloaded the Native Apps application there, which you can actually click on there later. I think I've just got the right link there. It was in, in Flash before, and then Adobe discontinued Flash because of all the problems with it, but they've updated it to run on something called Ruffle or something like that. So you can run web versions of these again. But anyway, let me bring up, get the mouse over here, let me bring up this app here. And let's see, I think I've got it on this screen now. Okay, so get out of the way, window, and there it is. Here we go. Okay, so I will go to, this is fine, look at all these cool things, it's fantastic. I want to go to Renaissance Astronomy Planetary Orbit Simulator, here it is, and I can voila. And so we can play around with Kepler's first law here. Let's show the empty focus. There's the empty focus. Let's show, let's draw radial lines to the planet from both foci. And then I can do things like grab this and move it around. And the point here is if I add R1 and R2 together, it's always exactly the same number. That's what makes it an ellipse. And notice, by the way, that R1 plus R2 is 2a. It's twice the length of the semi-major axis. In other words, it's equal to the length of the major axis. Well, you can see that's true because R2 is... Every time I say R2, I feel like I'm on D2. But anyway, R2, D2. As you can see, here's R2, right? And then here's R1, but this is also R1. So R1 plus R2 is equal to 2a, the whole major axis there. So R1 plus R2 is equal to 2a. No matter where you are. Soon we will make note then that, let's show this semi-major axis, semi-minor axis. Let's show the semi-major axis. If I move it over to where it's on one end of the semi-minor axis, well here R1 and R2 are equal to one another, but their sum is 2a. So right here they're both equal to a. R1 and R2 are both a. at the location right there. But their sum is always 2a. 2a or not 2a? That is the question. It is 2a, as a matter of fact. And around we can go, and then we do fun things like, why, let's animate. So there it is, always adding up to 2a. And notice, it's obeying Kepler's second law. In fact, it's built in to actually do it correctly. Look, it's moving faster when it gets closer to the sun, so it's actually making it do that. And there's a Kepler's second law thing we'll do shortly where it shows that too. And then we can do all kinds of other fun things after the break, because it is time to take a break right now. So, oh, it's so mesmerizing, I'll just keep that going while we're taking a break. Ten minutes. Okay, back to the salt mines. Play around a little with this. I can change the eccentricity, for example. Dial it up. This one only goes to 0.7. I wish it could go further, but here you clearly see that ain't no circle at that point. Here it lets us make parameters for specific planets. So let's do Venus. The eccentricity for, we'll have to do next. If we have to do okay. Venus, the eccentricity is only 0.007. So it's virtually a circular orbit. It's really hard. It's virtually circular. Earth. Anybody know what Earth's eccentricity is for its orbit?
0.8.
It's actually 0.02. Yeah, it's about 2%. So let's do Earth here. There's Earth, all right? If I take away the empty focus from being displayed, can you look at that and readily tell that it's not a circle? No. I think, careful look shows the sun's not quite at the center, but it looks just like a slightly off-center circle. So Mars, the one that Kepler used to convince himself that orbits are elliptical, Mars's eccentricity is about 10%. So here, in that case, if I show the other focus, right, you can definitely see that they're displaced from each other. But if you just look at the orbit itself, can you readily tell that's not a circle? I sure can't. Can you tell the sun's not at the center? I sure can. That's pretty obvious. But it's awfully close to just being an off-center circle. So why did it take so long for humanity to figure out that planetary orbits are not circular? Well, of course, they didn't first think they were going around the sun. But anyway, why did it take so long to figure out that circular motions weren't the key here? And part of it was that the ancient Greeks thought of the circle as the perfect shape. And they thought that the heavens and the earth, because it's not obvious, right? It's obvious to us, quote unquote, but it's not really obvious that earth and the heavens are the same stuff. And so they thought of the heavens as perfect and the earth as corrupted. And so heavenly motions should be perfect, and so they should be combinations of circles. Well, of course, we know that's not true now, but again, a lot of things are obvious in hindsight. So it was hard to tell that planets aren't on circular orbits because they're generally not too far off from circular orbits. And so they could do things like using off-center circles to do a pretty good job of explaining what they were seeing. Mercury also has a pretty eccentric orbit, but even still not that easy to tell that it's not circular. And I think they include Pluto on here. Yes, they do. So Pluto's got a higher eccentricity, but even still, it's hard to tell that its eccentricity is almost 25%. And now you start to see that it's kind of ovally. But it's not that obvious. It still looks like pretty close to being an off-center circle. Okay, let's move along to Kepler's second law. And let's make it nice and eccentric here. Let's go all the way 0.7. And so, and I'll move it over here to, what's this point? Aphelion, I'll move it to aphelion. And so I will sweep continuously, and I don't even know, sound effect, I forgot about that. I don't even know if we go to here. Let's see what it does. I don't know. But anyway, that's cute. And then we will start animation, and it'll start in equal amounts of time be painting segments of the orbit. So here we go. Start animation. Oh, is this Pluto still? Let's not use Pluto. Let's maybe use Mars. Yeah. Okay. I think I have to, because I don't want it to be a particular time. Let's. Oh, yeah. Let me just make it smaller. We'll just use things that are basically Earth-size orbit, but just different eccentricities here. And okay, so first let's go all the way down to. No, I'm doing the wrong one. There's so much pressure. Close enough. Okay, 1.02 U for the semi-major axis. Let's make the eccentricity 0 at first, and so then Kepler's second law isn't too impressive. Let's see, start sweeping. There we go. Okay, equal areas and equal times, but it's also just, you know, moving at a constant speed, and so not too remarkable in that case. Just pause that animation. Let's erase them sweeps there. Let's get it back over here to, oh, come on, that's just the right side. Every point is aphelion when you're on a circle, and every point's perihelion too. But let's dial up some eccentricity here. Let's make it, I don't know, something like that. And you'll start to be able to see that, I think it's to it. Oh, okay. Let's start sweeping after it gets on the other side. Boink. So you can start to see that some of the slices are a little broader but narrower, and other slices are longer, broader but shorter. Other slices are skinnier but longer, so to speak, right? Now, if we, let's pause that animation, let's erase the sweeps, and let's move it over here. Again, I wish it could go to higher than eccentricity of 0.7, to something like 0.95 or something like that, because comets can have very large eccentricities. But you'll start to see a pretty distinctive effect of Kepler's second law here, of it, a corollary being that it moves faster when it's close to the sun. Start sweeping. And, okay, I just have to do that. All right, so you see, whee! Right? Whee! Right? And if you, if I can really dial up the eccentricity, it gets to be, it's like, la 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 whee, la 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 la. So very eccentric comets, their orbits are very eccentric. They'll spend almost all their time very far from the sun, and then there's like a few months of glory when they whip around the sun, and then they might take tens of thousands of years to come back. So very long period comets will do that. Comet orbits can have very high eccentricities. Some of them are bigger than one. Some of them aren't even moving on ellipses. We haven't gotten there yet, but they're moving on hyperbole. For example, Oumuamua, and there's another one discovered recently. I think there's been 3 so far. They're from beyond the solar system. We know that because they're not on elliptic orbits, so they have enough energy that they'll escape the solar system on the way out, which means they came from beyond the solar system on the way in. They're from other star systems. They're escaping other star systems. That's crazy as hell to realize that. Now, if you're a weird Harvard astrophysicist, there's one weird Harvard astrophysicist who keeps claiming that they're alien spacecraft. Don't take that very seriously. See, any of you watch, I think her name's Angela Collier. She's got a YouTube channel where she's great because she's got a PhD in physics, and she just riffs, and she'll make these videos, they're like an hour long, and she's just like riffing, just talk, and at first you think this is going to be boring. No, she's magical. She just keeps your attention just riffing. So she made one about this, about that Harvard astrophysicist, where she's just tearing. She's so you need to look her up. Collier. That's how you spell her last name. All kinds of stuff she talks about, quantum mechanics, all kinds of good stuff. So, yeah. Ooh, magic. Ding, 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 ding. Wow, it's a big show. All right. Okay, anyway, let's see, and then anything else to do with this one? Yeah, probably not. Okay, so on to Kepler's third law. So let's pause this. On to Kepler's third law. So shrink that and unshrink this. How? Where's this? Let's see. Escape get you out of that. Oh yeah. Slideshow. There we go. Okay. Kepler's third law, which is my favorite because it's also called this. The harmonic law, or as I like to say, the harmonic law. Kepler's third law took him 10 more years to publish his third law in a book called Harmonica Mundi, which is like, I think that gets translated as like the harmony of the spheres and the harmony of the worlds, the music of the worlds, the music of the spheres, something along those lines. The square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. Or in other words, p squared is some constant, k we'll call it, times a cubed, where p is the orbital period, the time for one complete orbit around the sun, a is the semi-major axis, k is a constant number, the same for all planets. If we express p in terms of Earth's orbital period, i.e. in Earth years, and a in terms of Earth's value, i.e. in what we call astronomical units, abbreviated AU, where 1 AU is 149.6 million kilometers, which you should know. Everybody should know this, but especially astrophysics majors ought to know that 1 AU is 149.6 million kilometers, 150 million kilometers, 93 million miles, essentially. Earth's orbital semi-major axis. Well, then we got p squared equals a cubed, because do the math with me. If we do it for Earth, just Earth, what if we use years as the unit? What is p for Earth in years? 1 year, right? So it's 1, okay? And if we express the semi-major axis of Earth's orbit in terms of the semi-major axis of Earth's orbit, the AU, what is A for Earth in these units? A is the semi-major axis. So just 1 AU, right? So in these units, it's also 1, right? Okay, so let's solve for k. 1 squared is some number we need to determine k times 1 cubed in those units. What's 1 squared? 1. What is 1 cubed? Amazing. So solve this, right? See if you can do it in your head. 1 is k times 1. What is k equal to? 1! There we go. So these are very convenient units. P squared is equal to a cubed in those units because k is just 1 in those units. Does this mean that Earth is somehow unique and special? No, well, Earth is unique and special, but not for this reason, right? In other words, if we lived on Mars, then we could use the Martian orbital period, call that 1. We could use the Martian semi-major axis, 1, I like to say, Mars-astronomical unit. And then for Mars, you would say 1 is k times 1 cubed. Well, you know, Mars, you'd say 1 squared is k times 1 cubed, and you get p squared equals a cubed for Mars units too. The point is, there, pick a planet as your standard, express every other planet's orbital period and semi-major axis in units of that planet's orbital period and semi-major axis. And you'll have p squared equals a cubed. You just have to pick a planet and be consistent and express everything else in terms of P for that planet A for that unit, P squared will be equal to A cubed in those units, is what it comes down to. So Earth is not special in that way, it's just we live on Earth, it turns out, and so we just use it as the standard, but any planet would be the standard. Of course, with Earth as the standard, P for Mars is not 1. It's almost 2, and it's A for Mars is like 1.42 or something like that. So, but you plug in Mars's orbital period in Earth years, Mars's semi-major axis in terms of AU, and then P squared over A cubed for Mars in those units. But in its own units, if you will, it'd just be 1 equals 1. Does that make sense? See what I'm getting at there? You can use any planet. We just use Earth because we live on it, is what it comes down to. Later we'll see how you can do this in like SI units, and then it becomes P squared is equal to 4 pi squared over the gravitation constant times the sum of the mass of the two objects orbiting one another times A cubed. It's a more complicated coefficient there, that's what K is in general. But if you use funny units where time is in years and distances are in AU, that funny combination of units, 4 pi squared over G times the mass of the sun plus the mass of the Earth, in those units is equal to Y, is what it is. Okay, can I push the magic? Oh, sorry. What questions do you have? Or comments or observations? Okay. I forget what's next. What's going to come next here? Yeah. Okay. So, you know, if we made measurements and made a plot, right? This graph shows Kepler's third law, P squared equals A cubed holds true. The graph shows only the planets known in Kepler's time. In other words, if you want to linearize the plot, if you want to get a straight line plot, well then plot A cubed on the x-axis and plot P squared on the y-axis, and then that'll be a straight line, y equals x, right? And so the way to test it would be to make a plot of every planet's P squared and every planet's A cubed, plot them against one another, and they should fall on a straight line. Sure enough, they do, right? So here's for the inner planets, Mercury, Venus, Earth, Mars. Here's for Jupiter and Saturn. They follow a really, really nice straight line if you do that, because, well, it turns out P squared really is A cubed, to an awfully good approximation. This graph, based on Kepler's third law and modern values of planetary distances, shows that more distant planets orbit the sun more slowly. So if you plot average orbital speed, because it's varying, but you average it, versus average distance from the sun, then you get a plot that looks like this, that nearer planets go around the sun at greater speeds, right, if they had odometers, than further planets do. And that also follows from Kepler's third law. If you do the math, the planets that are closer to the sun are moving around it faster. And it's not just because the orbit is smaller, it goes beyond that. Not only is the orbit smaller, but the planet itself is moving faster. And so Kepler's third law produces the precise details of all of that. Now, later on, we'll talk about dark matter in the universe, and we'll talk about how in a galaxy like the Andromeda Galaxy or the Milky Way or any spiral galaxy, it looks like in photographs, and even more so if you look with the eye, it looks like most of the mass is concentrated at the center, in which case you should get that objects orbiting the center of the galaxy should behave approximately like planets do in our solar system. The further away from you are from the center, the slower you're moving in your orbit. But when Vera Rubin actually made the measurements using the Perkins telescope in Arizona, she discovered that actually all the objects are moving at just about the same orbital speed once you get not too far away from the center. And the explanation is there's extra mass making things move faster in their orbits than they would if WYSIWYG, if what you saw is what you got, so to speak. And so you got a fundamental discovery out of that, that's what appears to imply that there's dark matter in the universe. And by the way, this is jumping ahead just a little bit. Some of you have told this before. You may know that there's much more dark matter in the universe, if dark matter really is the explanation, than there is so-called baryonic matter, the electrons, protons, neutrons, you and me kind of matter. And so sometimes people imagine that our solar system is dominated by dark matter, that we're surrounded by more dark matter than baryonic matter, and that's not true. Later on, you will do this calculation. It'll be a homework problem next semester, where you use the rotation curve of our galaxy to estimate how much dark matter is in the solar system, how much dark matter is in the Earth. Dark matter is very spread out. It makes up in volume what it lacks in density. It's very, very spread out. And the total amount of dark matter, based on the rotation curve, that should be within the body of the Earth is about 1 kilogram. It's about 1 kilogram. So where we are is utterly, completely dominated by baryonic matter. The reason why dark matter dominates overall is because we have these gigantic dark matter halos around galaxies, both above and below the plane of the disk if it's a spiral galaxy. And so all that volume of very low density dark matter adds up to being more total mass than by quite a bit, than by 5 or 6 times than the baryonic matter. But within the disk of a galaxy, baryonic matter dominates. You are not surrounded by lots and lots of dark matter compared to baryonic matter. If we were, we'd see the effects on, like, our orbits around the sun and stuff like that. So that's a digression, but fun fact, we're going to use these ideas, kind of ideas later to talk about stuff. What questions do you have? I don't remember if I'm using the next slide or not at this point. I am not. Okay, we'll get to that. These are conic sections and so forth. But now it's time to do some chalk and talk. Put some math behind, more math behind all of this. So let me turn the camera towards the board. And I gotta zoom out here. And I guess I'll just confine myself to that portion of the board here and turn on the lights. Oh, you gotta be kidding. Okay, I think well, these are, yeah, cool, okay. Everything's better when you make it a nice digital panel, It just makes no sense to have, like, switches that are very reliable like that. You really want to be able to, like, if I want to change the lights, why would I want to do this like I could before? Why would I not want to, like, walk over here and, Okay, anyway. So, let's see. So let's draw a nice ellipse here. Well, let me attempt to draw an ellipse. Yeah, that doesn't sound too bad. By the way, I probably mentioned this to most of you before. You will often see that I forget that I should always draw a circle first and then locate the center of the circle. Because I'm not Dr. Trees. Dr. Trees can draw a point, draw a perfect circle around it with his compass arm, right? I cannot do this, okay? Anyway, here's my attempt at an ellipse. It doesn't stop. That's not too bad. Okay, so we'll draw major axis, minor axis. So there to there, what symbol does that get? That's A. That's A. Semi-major axis. Okay. And then there to there, what symbol does that get? B, it turns out, yes. B. Semi-minor axis. Okay, and then I'll just assume here and here are the foci. And we called this distance C before, but I'm just going to label it with what it is, right? Because remember, that the eccentricity was C divided by A. So C is AE. That distance from the center to either focus is AE. So I'll just label that as AE. And I'll say that this is focus F prime, and that's focus F. So F and F prime are the foci. Here are the two foci there. And we'll say sun is at focus F. We'll just assume that. Could have been at the other one, but we're saying it. And we'll say, okay, let's see. Here's our planet, or it could be a comet or whatever. And so, hope I hit my target. Not too bad. All right, hope this doesn't get too busy, but here is R, and I'm going to call this one R prime, the distances from the two foci to the planet at that moment. And remember, E is the eccentricity, such that 0 is less than or equal to E is less than 1. It's an open interval on the right side there, so to speak, for an ellipse. And this cute little angle here between the major axis and the location of the planet is going to be called theta. And as we were saying before, the equation of an ellipse is r plus r prime is equal to 2a. R plus r prime always adds up to the same thing, namely 2a, the length of the major axis. So this is expressing the fact that the sum of the distances of any point on the ellipse from the foci is constant. Expressing that sum of distances to the two foci for any point on the ellipse is constant. That's what makes it an ellipse. That's not true, that ain't an ellipse. So I'm going to consider now a point on either end of the minor axis. So there's B, there's R prime, if I make that one F prime, there's F, that's R. And as we mentioned before, we consider a point on either end of the minor axis for a point on any end of the either end of the minor axis. We have that R equals R prime equals A. Since R plus R prime is 2A, and they're equal to one another, they're both equal to A at that location. Buying what I'm selling? Happy with that? Okay. So at that location, R and R prime, and also on the other end of the minor axis, are both equal to A. So let's kind of zoom in here. So I'll draw this bigger here so that you can see it. So theta right there. Oops. That's R prime, this is R. Okay. Let me make a triangle. So here's a right angle right there, and here is a long, skinny triangle then. At this place, it wouldn't have to be long and skinny, but as I'm drawing it here, I have this triangle right here. Okay? So, what do I want to say here? So first I'll write the claim and then we'll show it's right. Oh, sorry, oops. I'm being silly at this moment, I think. Yeah, I was being silly. Okay, I'll get to that later. Sorry, I'll get back to it later. So let me draw this bigger drawing. This is one. I'm going to make another Pythagorean theorem later. Okay, so here's the two foci. Here's B. Here is A and A, because R and R prime are both A at that location. And this distance right here is equal to what? From the center to either focus is what in terms of A and the eccentricity?
AE.
It's AE. It's AE from over there. So this is AE. So hypotenuse is A, and the two sides are B and A. So we use the Pythagorean theorem. Pythagorean theorem. We've got that A squared is equal to B squared plus A squared E squared. That's just the Pythagorean theorem applied to either one of these two triangles. So hypotenuse is A, the sides are B and AE, so A squared is B squared plus A squared E squared. Or in other words, we get this very fundamental relationship here. B squared is equal to A squared times 1 minus E squared. Why, that's good enough to get a box around. B squared is A squared times the quantity 1 minus E squared. Just solving that for B squared there. B squared is A squared minus A squared E squared. Factor A squared times the quantity 1 minus E squared. If E equals 0, what does that say here? If E is equal to 0, how are B and A related? They're the same. If E equals 0, B equals A. Does that make sense? Because that means it's just a circle, right? It's just a circle, right? Circle. So that's consistent. Circle. If E approaches 1, what happens to B? It approaches. If E became 1, B would be 0. Yes, 0. 0. And that's this idea of it's just degenerating to a line in that case, right? There's no thickness perpendicular to the major axis. So we just get a little line segment in that limit. But as we'll see, we say really that when E is 1, it's become a parabola. Which doesn't really follow from anything we've said, it's true. It degenerates to a straight line segment there. What questions do you have? Comments, observations? And I'm throwing my chocolate away.
So this is only when the R's are equal, right?
No, see the thing is we derive this relationship here, but A is just a property of the ellipse. It doesn't care where any of the points are, right? B is also a property of the ellipse. These are just the lengths of the major and minor axes. And E, it's a property of the ellipse. So this is a general relation that we've obtained from the specific case of the point being right here. But this is just a property of the ellipse, right? That we derive from this location right here. You could derive from other locations, but here's where it's nice and easy. Good question. What other questions do you have? Okay, so let's get fancy and derive the equation of the ellipse in polar coordinates, because that will be very useful to us. I can hear the celebrations happening in the background there. You all love polar coordinates, right?
Oh, yeah.
Good. Glad to hear it. The equation of the ellipse in polar coordinates. Equation of ellipse in polar coordinates. So, here's where I'm going to do that other figure I was going to draw before. So, I should take advantage that I've got like a built-in axis here. Okay, so this may not be really where the focus I would be. I don't care. It doesn't really matter. Okay, so I'm going to, this point right here, let's say. Okay, so then, how do I want to do this? I'm going to say, here's R prime. Here again is R. And this angle of the point, the planet could be there. That angle right there is theta. So that's the angle away from perihelion of the planet, if you like. But also it's just like some point on the ellipse. Okay. Then, okay, what is that distance right there? It's twice the distance of either focus from the center. The distance of either focus from the center is what again? AE. So that distance is 2AE. 2AE. That's 2AE. And I'm going to draw the perpendicular right here. There's a perpendicular. Maybe I'll do it like this, so I'll use that kind of designation. So what's that distance? What's this kind of height, if you will, of the planet, of that point above the major axis? So this is R. That angle is theta, so this side opposite angle theta, where the hypotenuse of this little triangle is R, why that's equal to where every is a syllabus. Fill in the hms. R sine theta, right? R sine theta, that's R sine theta. There's the side adjacent. R cosine theta. Right? So now we've got us a long skinny triangle. It wouldn't have to be long and skinny, but I made it long and skinny because I wanted to. So here's this nice long skinny triangle. For that long skinny triangle, Pythagoras speaks to us from beyond and says hypotenuse squared is the sum of the squares of the two sides. So R prime squared is equal to 2AE plus R cos theta, the quantity squared, right, from here to here, 2AE plus R cos theta. Quantity squared plus R sine theta squared. So squared theta. Make sense behind what I'm selling? So, some of you have heard me tell this story too, maybe all of you. I learned, some students informed me once that they were in a class with Dr. Nunemacher and they talked about FOIL, and Dr. Nunemacher's response was, "What is FOIL?" Which is amazing, because a talented mathematician had never heard of FOIL. This is similar to my experience one day when I saw this over and over again on students' papers, and I'm like, what the hell is that? And so I told them that, and they said, it's SOHCAHTOA. And I said, I repeat my question, what the hell is that? Right, well, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. I had never heard of this before. Nobody ever told me that before. It's that little mnemonic there. And yet I certainly knew those relationships. And similarly, you can rest assured that Dr. Nunemacher knows how to multiply binomials together, even if he never used the FOIL mnemonic. And so in his honor, whenever we wish to expand the binomial, I will refer to it as Nunnemacherian multiplication. So here we go. Let's do a Nunnemacherian multiplication, maybe called Nunnemacherian expansion, and E for short, of this binomial here. We're squaring that binomial there. This turns this into, well, this will be 4a squared e squared plus r squared cosine squared theta plus 2 times the product of those terms, 4a r cos theta plus r squared sine squared theta. 2, 4, 6, 8, time to factor. Not a very good time. So let's factor this. This is, and if I, if ever I'm doing a calculation, I screw up, just, it can happen, even if I'm working from my notes. So this turns into r squared cosine squared theta plus r squared sine squared theta. So this is r squared times cos squared theta plus sine squared theta plus what do I want to say? 4 a squared e squared plus 4a e cos theta. Quick! What is cosine squared plus sine squared of any angle? 1. So this just turns into r squared plus, and then both of these terms have 4ae in them, so let's factor that out. Plus 4ae times ae plus r cos theta. And then we can say, since we know that r plus r prime is equal to 2a, well, that says that r prime is equal to 2a minus r. And so therefore, another way to write r prime squared is that it is equal to 4a squared minus 4ar plus r squared. And so if we look over here and we use that fact, we would have, then we could also say that this is 4a squared minus 4ar plus r squared is equal to r squared plus 4a. Oh, look, r squared's canceled. Factor on the left-hand side. and we say, okay, so 4a times the quantity a minus r, because we can factor the left-hand side, we factor 4a out of both terms, is equal to, right-hand side was 4ae times ae plus r cos theta. Oops, cos theta, r cos theta. Well, now we can divide through by 4a and say that a minus r is equal to a e squared plus e r cos theta. We're going to go ahead and divide by 4a and then actually re-expand the right-hand side there. Pause for a moment to let you catch up. Because I'm like, wait, I'm 3 steps behind that. So, yes? This one right here, probably. Yes. Yep, thank you very much. Yep. Yes, like I said, please, if I do that, let me know. Don't assume that I don't make mistakes, because it turns out I do occasionally, right? Yes, and as I like to say, there are 14 things that I do not know. But one of them is how many things I actually don't know, so I'm covered. All right. So, turns out it's more than 14, I suspect. But anyway, okay. And so then rearrange this. This says a, so bring that ae squared over, I'll just be very explicit. A minus ae squared is equal to, what would it be, r plus er cos theta. Or in other words, a times 1 minus e squared is equal to r times 1 plus e times the cosine of theta. But to write something, to write the equation of the ellipse in terms of polar coordinates is to specify r in terms of theta. How far are you away in terms of what angle you're at? And we got it right here. We can solve now. So r is equal to a times 1 minus e squared divided by 1 plus e cos theta. Cos theta. Another box-worthy equation. There it is. R equals a times 1 minus e squared over 1 plus e cos theta. This is, in fact, the equation of the ellipse in polar coordinates. This is what our goal was there. And thus there is much rejoicing. Ooh. Ooh, let's practice that. Isn't that beautiful? It makes you want to say, ooh. B. I'll give that a B. I'll give that a B. We'll work on it. It's good. It's good. But we'll do that later. There it is. That is r as a function of theta. And so, in other words, how would you actually use it to plot the ellipse? Well, you'd say, okay. Oh God, that sucks. Something this might be getting in my way. Okay, so I'll do this like, about, not too big. Yeah, I'll go with that. Yeah, okay. So then the idea is, right, that for any value of theta, you can imagine stepping along for different values of theta, and you'd plug into that formula to figure out how far along you go in order to plot that point. So for every value of theta, there's r as a function of theta. So you can imagine stepping along, tell your computer program, do this theta, what's r for that theta? Do this theta, what's r for that theta? So for every value of theta, whatever it is, we would focus. So in other words, you've got a focus at the origin, and this is how to draw the ellipse based on that focus. Note that we put the focus, if it's for a planet or asteroid or like the sun, at the origin, and use our formula to compute how far away the planet is for each value of theta. How far from sun to planet, or focus to point, it could just be a pure math problem, from sun to planet for each value of theta. So it's possible to write the equation in Cartesian coordinates, but it's really better to use this polar coordinates to specify what it is. And, okay, so I'm not going to charge extra for this. A couple of more minutes of quality education right here, because I just got one little more thing to say. Perihelion and aphelion distances. Very simple. And then we'll be at a good point for starting next time with gravity. Perihelion and aphelion distances. So, I keep redrawing them. How are we going to do this time? Not bad, not bad, not bad. Same D, right? So, here is the perihelion distance, and notice that for the perihelion distance, that, what do I want to say? RP is equal to A minus AE, because from here to here is A. That's A. No, it isn't. What am I trying to cover? That's A plus A. I'm messing myself up here. Let's see. RP is A minus AE because I'm being stupid. Okay. Yeah. This. What's that distance right there from the center to the perihelion? That distance is not a number, the symbol. Yeah, it's the semi-major axis, which we're using the symbol A for, right? That's A, and now and this distance from the center to either focus, why that's C, which we said is AE, that's AE, right? So the perihelion distance is A minus AE, is what I was trying to say. So RP is A minus AE is the part left over there. Or in other words, the box-worthy equation is the perihelion distance is A times the quantity 1 minus E. Which again, just it's very useful. Shows up all the time. And then finally, if we want the aphelion distance here on the other side, right? So the aphelion distance, so sorry for the clutter, there's our P. RA would be, there's RA, the aphelion distance, good God, is going to be A plus AE. Because it'll be here again is A, add AE to that, and you're from that focus to the far side. So A plus AE is the aphelion distance. So RA is A times 1 plus E. Right, so it's nice, kind of symmetric looking. The perihelion distance, you multiply A by 1 minus E. The aphelion distance, you multiply A by 1 plus E, and we're done. That's it for this week. What questions do you have? Yes?
This is like all in the textbook, right?
It is.
I mean, like in terms of like.
Yeah, it's all in the textbook, that's right, yes, absolutely, yes. Yeah, for sure. Yeah. And again, so this guy was but, you know, just to be clear, right, so for the aphelion distance, look, center to the aphelion, that's A. And then if you get to that other focus, that's AE. So A plus AE is the aphelion distance. But for the perihelion distance, well, we've got center to the perihelion, that's also A, but we're subtracting now AE from that to get the leftover to be the perihelion distance. So it's not actually complicated, even if I mean it sounds subtle and complicated. It ain't. It's simple. See you next time. So how was your trip?